Welcome back. In today's problem, we're trying to find the energy of the signal y of t. We see that x of t is the time shifted unit, is the difference between two time shifted unit impulse function. We know that for a unit impulse function, we know that will equal 1 when t is equal to 0 and 0 when t is less than 0. We know that if we integrate the unit impulse function, we get the unit step function u of t, which is equal to 1 for t greater than or equal to 0, and 0 for t less than 0. By knowing this, we can then see that the unit impulse function is the first difference of the unit step function. So if we integrate the unit impulse function, we then end up with the unit step function. In this case, we see that y of t is going to equal y of t is the integration of x of t. Thus, we know that we're going to end up with some time shifted version of a unit impulse of a unit step function. So we end up with y of t if we integrate x of t. Thus, that is going to equal to, and we integrate by parts, and not actually in parts, but we break this up into two sets of integration. And one is the first expression of x of t dt. And in this case, we change the independent variable in the signal x of t to tau. And that is going to be minus the integration from negative infinity to t. And we do the same with the second expression in the signal x of t. Doing this integration, we end up with the difference. We could probably just do the full integration, but integration is, I think, easy for us at this point in time. So that is going to equal to t plus 2 minus u of negative infinity. Negative infinity in this case, u of negative infinity in this case is because when we take the limit at which u of t and t becomes, our tau becomes negative infinity plus 2 is still negative infinity. We do the same thing for the other side, and we get u of t, tau becomes 2, tau becomes t, and that is minus u of negative infinity. We see that u of negative infinity cancel out, and we end up with the two time shifted versions of the unit step function as written, and this is y of t. Excuse me. Before we move on, we know that u of t, the graph of u of t looks like the following: 0, and this is t. We have the following. So again, we see that the graph is 1 for t greater than or equal to 0, and 0 for t less than 0. So we have the difference between two time shifted version of the unit step function. So we can do this graphically by saying that in this case, the signal u of t is not inverted. So thus, it is not, it doesn't come straightforward, because if we advance something means we push it further in time. But in this case, if we push something further in time, as in like if we push this unit here, if we push this function further, say positive 2, that is not advancing it, that's actually delaying that signal. Because if it occur at 0, it means that it occurred before positive 2. So if we pushed it negative 2, that means we advance it in time. It's not straightforward. Into the intuition of this kind of movement of signal isn't really intuitive. But in this case, we see that if we delayed the signal by 2, and then we end up with a signal at 2, and if we advance the same signal And let's use a wiggly squiggly line for this one. And if we delayed it, and if we advance it by 2, we end up with u of t plus 2. And this one over here is u of t minus 2. In this case, if t, for this signal, if t becomes -2, then the unit impulse, the unit step function goes back to its original place, located at 0. So we then see that the signal y of t is the advanced unit step function minus the delayed unit step function. So thus we subtract this portion. So thus we end up with the rectangle here. And that is the unit step function. Y of t is going to equal 1 for t greater than or equal to -2 and less than or equal to +2. We can then state the equation for the energy of a signal, and in this case, a continuous time signal, and that is going to equal to the limit at which t approaches infinity, and we integrate the signal x of t, the absolute value square, we integrate the absolute value of x of t squared from -t to +t. And in this case, this is y of t squared dt. We then see that outside of that interval, the signal will be 0. So it's only right we integrate for when the signal equals 1. So thus we see that the integration, so the limit at which t approaches infinity for that signal, if we integrate, we get 1, and 1 squared is 1. So thus that is equal to -2 to 2, and y of t is 1, so 1 squared is still 1 dt, and this expression evaluates to be 4. Thus, the limit at which t approaches infinity, we do not have a time variable approaching infinity, so thus the energy for this signal is equal to 4. They did not ask us to calculate the average power, but we know from the previous videos that the average power, in this case for a signal with the energy less than infinity, will have the average power equaling to 0. And in this case, we took the energy over a finite interval. Thus, we have a finite amount of energy, which is less than infinity. If we took the energy for the signal over an infinite interval, thus we have infinite amount of energy. And by having infinite amount of energy, the average power will be greater than 0. In this case, the average power is 0, and that could be proven by the limit at which t approaches infinity, 1 divided by 2 of t, and we run that sum from we integrate in this case from -t to t, and the same thing, the absolute value of y of t squared. This we know evaluates out to be, in this case, if we change these to -2, this is going to be 4. And thus we see that 1 divided by, in this case 4, that would be 2 over t. And as t approaches infinity, this goes to 0. Might move a little bit fast, but in this case, that is why the average power is equal to 0. See you in the next video. Bye.